Spreadsheet Lesson 9. In this lesson, we will pick up where we left off in our maximum volume problem. Last time we considered the volume of a cylinder that you could reach if you optimized the radius and height given a limited area, and we discovered that the radius and height would be about equal and produce a maximum volume if the area was limited to 324 units, about 633.23 units. So the question now becomes, what if it wasn't a cylinder? What if we did, for instance, a cone, like an ice cream cone? So you've got the sides of it, but you don't have the little round part at one end. So the first thing we're going to do is we're going to use the same basic approach for the cone. So here in the spreadsheet, we are going to duplicate this spreadsheet, just like we did when we went from multiple choice grader to multiple choice and free response grader. We're trying to keep a lot of our prior work. So we duplicate it, and again, like that. The only difference between these two sheets really is their name to start with. So the first thing we'll do here is we'll rename this as cone. And now none of these equations here will apply. So we're going to highlight those and hit delete. And also we'll highlight that just by clicking on it and hit delete. You probably don't have that on yours, and that's fine. But you want this area clear. Now, one thing I want to point out about this is you may think, oh my gosh, I lost a tremendous amount of work here. But you actually didn't. Believe it or not, the conditional formatting is still functional here. And this max equation, you didn't delete that. It's just that when these are all empty, the maximum value really is 0, but none of them actually equal 0. So, yeah, it's kind of a nice way of preserving some of your work. We also want to reset this to start at a guess of 1 with steps of 1. So now what we need to do is we need the mathematics to put in here that can calculate the height of a cone with no circular closing on it of area 324 and radius of 1. So we need this height equation again. We're going to go back and do a similar thing, but this time we're going to start with the equations that concern a cone. And just like last time, we're going to have to remove from this equation the part of it that is this circular base here. That area right there is pi r squared. We know that because we know the area of a circle. And that is embedded in this area equation here, but it's not immediately evident. What you have to do first, you have to distribute this pi r over, and then you realize this pi r times that r will give you pi r squared, and that's what you want to eliminate from the equation. But this pi r distributes. It doesn't just go to that portion, it also goes to this. So that gives us pi r times the root of h squared plus r squared there. And this is actually the area we want to work with. I'm going to rewrite that over here because we're going to have to do some algebra on it as well. So the area of just the cone portion without the circle on it is pi r times the root of h squared plus r squared. And then I'm just going to go in here and delete that because it's in my way. So now we have this equation for area, and we have this equation over here for volume. And what we want to do is first solve this equation for h so that we can find the h when we know the r and the a. So the first step of doing that algebra is simply divide both sides by pi r. So we're going to have a over pi r. And that's going to give us this square root thing here, which we're going to get rid of by squaring. So we're going to square both sides. So because this is h squared plus r squared. I'm actually going to stop talking for just a few seconds for you to establish in your mind that I've done this algebra correctly. So that should make sense to you, that this so far is the correct, that these two equations express the same relationships. Next, we're going to subtract r squared from both sides, and then take the square root of both sides. So we're going to end up with h is equal to the square root of a over pi r, all that quantity squared, minus r squared. So again, I'm going to pause. I did 2 algebraic steps in a row there, but I'll give you the opportunity to establish for yourself that this is in fact true. So this is the equation we want. So what I'm going to do now is I am going to highlight that here. Oops, I didn't quite do that quite like I wanted to. Let me do it like that. highlight that here. Control C to pull that out. And then I need to go into my spreadsheet and go Control V, drop it in, and make it smaller. And this is something you won't have to do. I'm just doing it because it makes it easier to show you how everything goes together if I have the equation right on the page with me here. I'm just going to move this over like this. Here's the equation we want to implement here under height. So we have a function that will give us h if we know a and r. Now writing this in Excel is a little bit tricky. So we're going to start off, we have to put in the equal sign, and the way you take a square root in Excel is it's also for a function, sqrt, and whatever's inside of these parentheses, the square root of that value will be taken. So this gives us the square root of, and then we need another set of parentheses under basically you can think of these outer parentheses as being like this radical that's on top of here. So we need another set of parentheses here to get this done. It's going to be our area, which, by the way, we were going to want to put dollar signs in. So function F4 there. Oops, I did control F4. Function F4 there. Okay. And then we're going to divide that. And remember, in Excel, it's a good idea to put parentheses around your denominator. So I'm actually going to put parentheses here. Pi times r, that's that radius. And then I'm going to close those bottom parentheses, those parentheses around pi r. Then I'm going to close these parentheses around the a over pi r, so that's a over pi r. Close those parentheses. And everything inside of those parentheses, these two that have the gray on them here, those are these two here, all of that stuff inside of there has to be squared. So far, we're going to take the square root of something that's incomplete. If you look at your parentheses, we've got an open parenthesis here that doesn't have a closing parenthesis to match it. Remember, think of this parentheses next to sqrt as being like this is the beginning of the radical. We haven't closed the radical yet. We have this parenthesis is closed by that one, this parenthesis is closed by that one, and this parenthesis is closed by that one. And that's one of the challenges when you're writing these in Excel, is really keeping up with all the parentheses you've got. But anyway, so now we need to subtract the r squared, and then we can close our square root. So we go minus r again over there, and this time we want to square just that part. Now we can close the final parentheses here. And again, it gives you these the shading to help make it clear that this parenthesis is matched by that one. So now we're going to take the square root of the quantity area divided by the quantity pi r, all of which is squared, subtracting the radius squared. We're going to take the square root of all of that. So when I hit enter, that should give me the value. Now, it has a suggested autofill. If you're like me, sometimes you like to check your equation before you do the autofill. So I'm going to go ahead and click X here and just double check that this makes sense. So it's the square root of that thing in orange divided by pi times that thing in purple, all of that squared together, then subtract the purple thing again, squared, and then take the square root. So yeah, that is right. So now we can drag it down and see if this makes any sense to us as well. Certainly as the circular portion of the cone, the circular end of this cone is small, that's going to make it a very tall, thin cone because all of the, well, it begins as a really small circle and then goes to a point. So all the area has to be stretched out a long way. But as you make that radius larger, you're going to have to make the cone shorter because it's going to kind of go from being like well, I don't even know how to describe it, but it's going to be short and fat down here, a really big circular area, and almost like a plate here, this shape would be, whereas this would be much more like a tube almost, except for it tapers to a point. So it makes sense. As the radius goes up, the height goes down. So far, so good. Now, the volume. The volume, let's go back over here. The volume is pi r cubed h over 3. And really, that over 3 you can put anywhere. Some people say it's 1/3 pi r squared h. Lots of ways to say it. But we're just going to pi r squared h, all multiplied together, then divide all that by 3. So let's go back into here. It's going to equal to let's just start a parenthesis for our numerator, pi times r, in this case it's cubed, no, squared, I'm sorry, squared, times h, all of that divided by 3. Pi r squared h divided by 3. And again, since the area is not part of this equation, I don't have to worry about any dollar signs in this one. Hit enter. I'm going to accept the autofill because I actually know that is correct. So, what do we find? Well, the first and amazing thing we discover is that the area, the volume enclosed by even the non-optimized cone is notably larger than the maximum optimized area you can get from a cylinder. A cylinder only encloses 633, but a cone with the same area can enclose over 677. Now, of course, what we want to do here is zoom in and stuff to find out. So we do the same thing as we did before. Let's go to 7 to start. This gives us errors down here because you've got negative numbers appearing underneath your radical. But that doesn't matter. We're going to change our step to be 0.2. And so we find that the maximum was actually a little less than having the radius of 8. Now we're up to 680, which is cool. Let's change to 7.6 up here, 7.6, and make our step be 0.1. And we're still getting 7.6 is still a good place to start. Let's try going to 0.02. All right, now we get 7.7, so slightly higher than 7.7 is where our maximum is. And then let's change this step to 0.01. It's like 7.71 is a good starting point. And we'll increase by 0.002. Looks like 7.716 gets us an area of a volume of 680.4486, 0.4486. It's one of these two in here. You could continue to zoom in. We could change this to 7.714 and then change this to 0.001. But at this point, it's kind of academic. You're talking about thousandths of an inch here on your radius, making something out here at the 10 thousandths, something like that, of a cubic unit. So what we find is the maximum volume enclosed by this cone is when the radius is 7.71 and the height is 10.91. Now this is kind of interesting. The diameter is twice the radius. So what's funny about this is that ice cream cones are kind of tall and thin. They really aren't optimized for the maximum volume compared to the cone. But that kind of makes sense. You want a certain cone volume balance here. What this is approaching is something that's like kind of bowl shaped. It's about 10 units high and about 14 units in diameter. So that's the way you would get your maximum volume for the cone. And the only really new thing we learned here in Excel in spreadsheets, we didn't learn anything new in spreadsheets. We just learned something new about which shape is better. Now, then you must ask, why do we not package things in cones? And the short answer to that is, well, a bowl's pretty good for carrying liquids, right? Anyway, that's the end of the spreadsheet lesson involving maximizing volume.